Green's theorem, Stokes' theorem, and the fundamental theorem of calculus share an identical underlying structure. Each relates the behavior of an object inside a region to its behavior on the boundary. All three can be condensed into this single expression. This is the generalized Stokes' theorem. It uses two specific components, the differential form, omega, and its exterior derivative, d omega. Walter Rudin's Principles of Mathematical Analysis provides a rigorous foundation for this unification. Chapter 10 develops these tools to replace standard vector calculus with a more powerful language. Differential forms are objects designed to be integrated. A zero form evaluates a scalar at a point. A one form measures flow along a path, and a two form measures the flux passing through a surface. Algebraically, we define a k-form as the sum of a coefficient function multiplied by a basis of differentials. This multi-index I tells the algebra which combination of coordinate axes we are measuring. While standard vector calculus is limited to 3 dimensions, this abstraction allows us to perform integration and differentiation in spaces of any dimension. To combine these forms, we use a specialized multiplication called the wedge product. It is an alternating product, which gives it properties distinct from standard multiplication. The first rule is anti-symmetry. Swapping the order of the differentials flips the sign. dx wedge dy equals negative dy wedge dx. Because of this sign flip, any differential wedged with itself results in 0. If you swap the identical terms, you're stating that the value must equal its own negative, which is only possible if the result is 0. Consider how this simplifies a basic algebraic expansion. When we distribute the terms, the dx wedge dx and dy wedge dy components vanish instantly. We are left only with the mixed terms, which combine into a single, clean expression. Swapping coordinates in a wedge product corresponds to a reflection in space. By flipping the sign whenever variables swap, this algebra automatically tracks the orientation of paths and surfaces. Differentiation is handled by the exterior derivative, d. It takes a k-form and produces a k+1 form by differentiating the coefficient function and wedging it with the existing differentials. This follows a modified product rule. This term, -1 to the k, adjusts the sign based on the degree of the first form. The most significant property of this operator is nilpotency. Applying the exterior derivative twice always yields 0. We can see why by looking at the second derivative expansion. Mixed partial derivatives are symmetric, but the wedge products are antisymmetric. In the final summation, every term is cancelled out by its opposite pair. Test this property yourself. Calculate the exterior derivative for this one form. The derivative is x squared dy wedge dx plus y dy wedge dz. This zero result for a second derivative is the analytical mirror of a geometric truth. The boundary of a boundary is always empty. To transform these forms between different coordinate systems, we use the pullback, denoted as phi star. While a standard map carries points forward from a domain to an image, the pullback operation takes a differential form defined on the image and pulls it back to the original domain. This allows us to classify forms. A form is closed if its derivative is 0. A form is exact if it is already the derivative of another form. Since applying the derivative twice always results in 0, every exact form is automatically a closed form. Using a pullback to convert a two-form into spherical coordinates, we replace Cartesian differentials with spherical equivalents and apply the wedge product. Antisymmetry rules eliminate redundant terms, leaving the Jacobian determinant to produce the volume scaling factor, r squared sine theta. This table summarizes the complete system, the alternating wedge rules, the nilpotency of the derivative, and the relationship between exact and closed forms. This algebraic framework provides the mechanics used to solve the generalized Stokes theorem, linking the local derivative of a form to its global behavior on a boundary. Next chapter, we will use these pullbacks to solve complex flux problems in Maxwell's equations.